Angelo Vermeulen was born in 1971 in a Flemish region called Waasland, and he attended the primary school in Sint Rochus in a city called Sint Niklaas. I know, I was there. And in that school, he led a small band of friends who were planning on building their own rocket that would orbit the Earth. We were like 11. The rocket never saw the light of day, but it was clear that Angelo Vermeulen had a fascination for space and technology. So he became an astronaut. No, not really. A space engineer. Not really. An astronomer. Not really. He became an artist, but always looked for the link between art and space. In 2009, he initiated SEED, Space Ecology's Art and Design, an international transdisciplinary network of artists, scientists, engineers, and activists. Vermeulen was a member of the European Space Agency topical team Arts and Science, and he was crew commander of the NASA-funded High Seas Mars mission simulation in Hawaii. He's making a PhD at Delft University. He has taught or been a guest at several universities in Europe, the US, and Southeast Asia, and he is a TED Senior Fellow. Ladies and gentlemen, I haven't seen Angelo Vermeulen for 30 years. Not a single mail, not a single contact. And now I find myself introducing him on this stage, reading his bio, and I think, well, Tim, what have you done with your life? It doesn't seem like a lot. Mind you, ladies and gentlemen, I do make a great spaghetti sauce. But for all your other stuff, here is Angelo Vermeulen.
Hello, everyone. Well, that was quite the introduction. It's the first time somebody talks about that rocket idea that I had when I was 11. So anyway, it's out there. Welcome, everybody. Today I want to share with you a project that I've been working on since quite a few years. What you see here in the back is not my project. It's basically images that were sent just a few days ago back to Earth. They're from the Hayabusa 2 mission, which is a mission by the Japanese space agency JAXA. And basically what you see there is a mission in which several rovers were landing on the surface, have been landing on the surface of an asteroid. They're bouncing around, they're photographing the asteroid, and the goal is, in the end, there is still a probe circling the asteroid to drop an explosive on the surface of the asteroid and then take a sample of the pristine core of the asteroid and bring that sample all the way back to Earth. Quite spectacular, a beautiful mission. We're really all over the solar system, which is tremendous. Now, what I'm interested in is the next step. The next step in space exploration, which is interstellar, traveling to different stars. The nearest stars are between 4 to 6 light years away, which, if you would travel, for example, with 10% of the speed of light, would take you 40 to 60 years to reach. So it's reasonable to imagine that sooner or later we'll be able to send probes there and we'll be able to travel there. Now, there's one defining feature of interstellar travel, which is uncertain futures. It is very different to design a space mission for an interstellar journey than in comparison to what we've done before. If you think about the Apollo space program, for example, when we were going to the moon, we would gradually, the way that it was set up was we would gradually go to the moon step by step, coming closer and closer to the moon, each time getting back to Earth and optimizing the system. And in the end, after several missions, Apollo 11 finally touched down on the surface of the moon. Now, with interstellar travel, this is not really possible. You can't just go a little bit interstellar, come all the way back to Earth, improve your system, and then go back. That wouldn't make a lot of sense, right? So what do? This is really a conundrum for an engineer. How to design a system for a challenge you actually don't know. That seems like impossible to solve, right? Now, we came up with the idea to embrace evolution and to use the concept evolution to solve this problem. And we're doing this with a whole team. At TU Delft, at Delft University of Technology, we're a multidisciplinary team. We're approaching this issue of interstellar travel from many different angles, and we've been working on it since the last 2 years. Now, what does that mean, using evolution? Well, the idea we're exploring is building spaceships or building concepts for spaceships that evolve and grow during their journey, almost like a living organism. Now, how could you possibly do something like this? How could you possibly create a structure that is evolving and growing over time? Well, you could do this using 3D manufacturing. It's already been proposed to use 3D manufacturing in space for near-Earth missions, because in this way, you could actually construct your infrastructure or other devices that you need in space at the actual location in space, instead of launching all the equipment from Earth. Now, if you're using 3D printing to print a structure in space, of course, you need resources. What kind of resources would be used? And for this, we came up with the idea of using asteroids as the actual resource for our spacecraft. So the concept is to mine an asteroid, take all those resources, and then start using those resources to gradually print a spaceship that can travel in deep space. Now, the idea of using an asteroid and transforming an asteroid into a space vessel is nothing new. This idea dates back to the 60s, where engineers were thinking about it, and it's still very present in science fiction. For example, the novel Seven Eves is an exploration of this idea. Now, what we're doing is we're taking this idea of transforming an asteroid into an actual spaceship, but we're doing the math. We're doing the engineering. This is advanced concepts research. And the first thing we decided was we wanted to use modular architecture, because modular architecture really enables you to create a structure which is gradually growing over time. Now, as a structural unit, we're using a truncated octahedron. It's a beautiful, interesting geometric shape which stacks really nicely. It has multiple sides to make multiple connections with the surrounding modules, and we're defining multiple different types of modules that are needed in a particular ratio to make the system viable. Habitation modules, life support modules, shielding modules, mining modules. So there's a whole range of modules that we've been defining, and we're creating a computer simulation in which we can investigate this idea. Here you can see an image how the architecture would actually evolve. So gradually over time, the interior of the architecture would be mined, which, as a consequence, the asteroid would be hollowed out, and then that empty space will be filled up with new modules, with architecture. So the architecture is really growing in two directions. It's growing on the inside of the asteroid, and it's also growing as a tail behind the asteroid. And the advantage of using this approach is that the asteroid is not just used as a resource for building materials and for developing the spaceship, but it's also used as a shield. Because when you're traveling with such a high speed through deep space, even the smallest particle might cause a big explosion. And so you have this interesting double function of the asteroid. The printing itself, we would imagine, would happen through mobile printers. Mobile printers that can reach all locations of the starship and can start printing new architectural modules. They would use a supply of materials, which you can see in the image on the right. You can see in space, you can see a module that is floating and is connected to the printer with an umbilical cord. And it's basically providing the printer with the materials to print with. Now, there are two main physical challenges when you're traveling in deep space. The first one is cosmic radiation. Very intense cosmic radiation can destroy your electronics, but also all life on board of your spaceship. Mind you, we're talking about a generation starship. we're not talking about an unmanned probe. We're really thinking about starships that where people actually live, and possibly for multiple generations during the journey. So the first problem is cosmic radiation. The second problem is particle impacts, which I already talked about briefly before. Even though deep space is close to vacuum, there are still particles there. And when you're traveling with a high speed, not only is the impact very high, but you actually capture quite a bit of particles during a specific amount of time. So how to deal with that? So far, we've been talking about a growing structure, an architecture that gradually grows and develops over time. With this in mind, with these two unpredictable challenges in mind, we're moving over to evolution. And of course, typical for evolution is that morphologies are very different and have evolved in very different ways to be optimized for very particular challenges, to be optimized for very particular circumstances. And that's what happens in nature. And it's the same idea we're using in our engineering. We're basically evolving our spaceship, our starship, throughout the journey, depending on the challenges that are coming ahead. And it is possible because you have all these modules, and you can move around the modules. You can basically reconfigure your entire structure. And you can reconfigure your structure in such a way, for example, if you're expecting radiation to come from a particular side, you can actually move over a lot of shielding modules to that particular side, and the modules that contain more sensitive contents, like habitation modules or life support modules, you can move them over to a different side. And so you can gradually reconfigure your spaceship to make sure that it handles the upcoming challenges properly. And this is a bit of a summary. So we're envisioning a starship that actually has a particular sensing horizon. It has sensors in front, and those sensors can gauge what's coming ahead up to a certain distance concerning radiation and particle densities. If what's coming ahead is very similar, the spaceship will just continue to grow because it works and it'll work in the future. If what's coming ahead is very different, then the spaceship would start to evolve, and it will reconfigure itself using genetic algorithms as an underlying technique. Now, like I said before, of course, we're not building actual hardware at this point. We're still in the mathematical stage, and we're building these computer simulations in which we can start to explore this kind of concepts. And ultimately, what we want to create is a virtual world in which we can generate a realistic deep space journey with realistic particle impact events, radiation events, and then start with a particular asteroid with a specific chemical composition and a small proto-starship connected to that, and then send the spaceship in this virtual simulation on its journey for example, 100 years. And then rapidly, you can see how the architecture evolves itself over time. And the kind of interesting experiments you can do with this is, for example, you could run the experiment again, doing the same exact journey, but with asteroids with different chemical compositions. And so you can start to discover under which circumstances this concept actually really works. The image you see here is a very famous image from the 70s by Gerard O'Neill. Gerard O'Neill was an advanced concepts thinker who was thinking about the future of mankind in deep space, and was very focused on creating actual space colonies, large-scale megastructures in deep space. And what you can see here is actually a tube that is spinning, and because it's spinning, it generates artificial gravity. And through the artificial gravity, because everything is being pushed on the inner sides of the cylinder, you can build entire worlds on the inside of the cylinder. Mind you, this is a huge structure. Nobody knows how this would be built, but as a concept, it's very interesting. And you can see a natural landscape and then a transparent part where the sun shines through. So these images were also very inspirational for us when we were designing this concept. And I basically came to the conclusion there's no point in researching a concept in which a spaceship that travels to a different star arrives on destination structurally intact, but everything inside is dead. That would not be a very successful mission. So we also need to get a better grip on how to sustain life in deep space, and that became the second component of our simulation. So what we're basically trying to do is we're using the asteroid as a limited resource that is feeding both the ecosystem and the architecture during its journey. Now, what kind of ecosystem would you imagine in deep space? What you see here is an existing ecosystem specifically developed for space by the European Space Agency. It's called Melissa. It's a project that has been in development for for almost 30 years. And it's a very interesting system. It's a fully circular system. It basically takes all wastes, all human wastes, which means toilet waste, CO2, sweat, and it breaks it down gradually through a sequence of multiple bioreactors with different bacteria, breaks it down into nutrients for plants, and then the plants provide oxygen and food for the astronauts again. And theoretically, you can keep people alive almost endlessly like this. Very interesting system, and I started working with them, and I thought, actually, we could use this system in our own research. And so we've been including the concept of Melissa in our system. What you can see here is some of the work of the architects and designers in our team. Like I said before, we're approaching this from multiple angles. We're approaching this problem of deep space exploration, of interstellar space exploration from multiple angles, not just through simulation and math, but also through visualization. And so what you see here is basically the work of Ari Zawan, one of our crew members, an architect, who tried to figure out how that ecosystem that I just showed you, the Melissa system, could be implemented in the spaceship. Next, I'm going to show you another clip, another visual. It's basically a short video clip. This was also the work of one of the architects of our team, Joris Putteneers, who made a visual impression of how a journey of a starship like this could look like. So, why do all this? Why think about deep future? I'm personally very passionate about deep future. I really want to contribute to that. And of course, in my lifetime, I might not be able to see the day of light of a starship, but it's extremely gratifying to start exploring ideas that could contribute to the future that maybe you might not live. When Tsiolkovsky, for example, the inventor of the rocket equation, was working on his math on space travel, there were no rockets yet. So that's one of the reasons I'm doing this. But very importantly, this kind of research really has ramifications for our life on Earth. First of all, when we think about circularity, this is really a key to our future. I'm not the first one to say this. Remember the ecosystem that I explained to you, the ecosystem from the European Space Agency. In such a system, every single molecule is important. and is being reused over and over again. And if we want to start a better life on this planet, taking better care of this planet, this idea of circularity is something we will have to radically start embracing. Secondly, there are multiple crises now. We all know that. There is political crisis, there is economic difficulty, even though recently, the last few years, things have gone up a little bit more. There's tremendous environmental issues, one stacking up on the other one. And nobody really has a clue where things are going. It's very difficult. Uncertain futures. And I think my main message here is, instead of regressing to old ideas, to top-down views, I think the only true way forward is if we become more adaptable and embrace evolvability to build a better future. Thank you.